Today, what we're going to be talking about is geotechnical considerations in design and construction of Tiltwall buildings and parking lots. I took out the section on geoforensics, and I'm going to do a whole presentation on the geoforensic part of it later. It's going to be an expanded version of it. So this is going to be mostly design and construction type talking for building and the parking lot. Audience, we got a lot of civil engineers, a lot of structural engineers, people from Harris County, City of Houston, and other cities that's going to be attending this thing. We got about 154 people or so RSVP'd. Geotech has been around now for 40 years, long time. We got about 60, 65 people, engineers, technicians, geologists, support staff. We work all over Texas, Louisiana, Oklahoma, Arizona, and New Mexico. We have our own rigs and lab. We're all set up full service. Again, if you need to reach me, that's my contact information. My email is de@geotecheng.com. My phone number is 713-699-4000. If you have questions as we go through this thing, again, I answer them as we go through. Type it into QA or chat, and I'll just answer it as I'll go through there. So, Tiltwall buildings are awesome buildings. They come on all kinds of shapes and forms and colors. And they're very practical, durable, and pretty buildings. I really like them. And a lot of commercial facilities, they use them throughout Texas. I mean, that's kind of seems like that's the favorite commercial type structure used throughout Texas. I guess I'll see it all the way Dallas, San Antonio, Austin, Houston. I've seen them, 4-story, 5-story Tiltwall buildings. From what I understand from the Tiltwall building, the manual, it says it was built in 4700 BC in Iraq when the villagers made walls from pressed mud. So I don't know if anybody remembers that. But they have loading ramps in addition to their buildings, parking lots, truck wheels, parking lots. They got big parking facilities subject to 18-wheeler loading. A lot of heavy traffic. The interior of them, you got all kinds of stuff in there. You can have shelving, you got boxes. You have these forklifts picking up this heavy stuff and carrying stuff running around. Typical construction sequences, of course, you do the earthwork, the mass grading, and remove the grass and weeds and trees, root raking, took out all the roots, start grading it. If you're doing moisture conditioning, you go in there, add water to it, to the soil as you put it back in, compact it to wet up the optimum. That's how you do the moisture conditioning for these things. To dig out the detention pond and put them on these pads. And then you go out there, start drilling your piers. And you go out there and start putting up your slab together. You put the steel and vapor barrier in after you build your pad. Then you go out there and start pouring your concrete in segments. Pouring pour strips. Then you start forming your panels and start having your panels done. Then you start standing up the panels. You can see standing up like that. Putting your columns in and your roof. Kind of how that goes. So beautiful structures and very practical. Puyo paving, design. You know, we do borings out there typically for 1-story type structures in the Houston area. We do borings, 25-foot deep for tilt wall buildings. If your soils are nice and strong. If they're bigger than that, multi-story type stuff, you'd go much deeper than that. Use a truck mount or rig, do the borings next to trees. Trees tell us the depth of the active zone by providing us with root fibers. Root fibers extend to the areas where there's no oxygen and water. That's where they die. And that kind of indicates the depth of our active zone. But that's not the movement active zone. They have active zone and movement active zone. Our active zone can be in Houston like 25-foot deep, but your movement active zone is only 10 foot. So these are root fibers. As you go deeper, become smaller. You do typically one boring every 3,000 to 10,000 square feet, depending on the size of the building. Sometimes, one every, 20,000 square. I mean, you got a 1.2 million square foot building, you do less boring than that. In Houston, it's about 25 feet. In Dallas and San Antonio, you may have to go 35 feet deep. Laboratory testing, you do all the standard testing, Heidelberg limits. You put water in the soil and when it becomes liquid in this cup. Take a sample of that, put it in this cup. You cut a groove through it with this thing. You turn the handle 20 to 30 times. And when the groove come close together, you take a sample of that. You get the wet weight of the soil. We want to know how much water is in the soil for it to behave liquid. You dry it up in the oven. You get the dry weight of it. You get to be measured how much water is in the soil. When it becomes liquid, you subtract the wet from dry. Then run a plastic limit test. In this test, we take the soil, roll it 1/8 of an inch. You get the wet weight of it. You put it in the oven and dry it up. You want to know how much water is in the soil for it to behave semi-plastic. When you subtract liquid limit from plastic limit, you get plasticity index, of PI. So if you got a project with the PI less than 20, you got low swell potential. Between 20 and 30, it's moderately expansive. Between 30 and 40, it's highly expansive. Above 40, very highly expansive. A couple other tests we do in the lab. We do hand penetrometer and torr vane. In a hand penetrometer, you push the hand penetrometer into the soil. You can read what kind of a strength it has. And in the torr vane, you put it at the end of the sample. You shear it in torsion. And you can read here what kind of strength it has. You can also do unconfined compression test. You can see the proving ring and the deflection, and you load up the soil to shear it. See how much load it can carry. You use that for your design of your piers, or your spread footings, or your strip footings, or auger cast piles. Use this strength value for your foundation design. One other test we do in the lab is called swell test. You take a soil sample like this, you put it in a ring like this, you cut it and put it in a ring like this. There's a ring here. You put it in this kind of a assembly in here. This measures the deflection. You put load on it with on this rack, equal to the geostatic stress. That's a load that's been in the ground, that's been used to. You add water to it. And of course, you add the load. And you basically, in the initial condition and initial void ratio or strain, you add water to it. Your soil is going to swell. When it stops swelling, you add load to it. Get to the same void ratio or same strain. That's your basically swell pressure. And this is the amount of swell you can have on your soil. Called a swell test. You use the ASTM method B. You add water, you let it swell. Do building pad. First thing you do clear and grubbing. Take out all the trees. Make sure you take out all the roots. You got to do root raking. Pull out all the roots and tree trunks. All these areas got to be demucked. You have to dig it out, remove the water, soft soils, replace them with on-site soils or structural fill, compacted 8-inch lifts, and test it. Compact 95% of standard proctor density. All this silty, sandy, soft soils have to come out. You cannot just push dirt into it. None of these organics got to be in there. No roots allowed in your pad. No roots in there. No organics. No tree trunks. All the organics have to be removed. You proof roll the ground after you remove the organics and stuff. You use textile item 216. You take a loaded dump truck. You go back and forth. We're not supposed to see any deflections here. And so, let's see. No deflections. This is not acceptable. Not acceptable. So you got to dig it out, draw it up, put it back in. Floor slabs. We have alternative floor slab treatments. We present these alternative floor slab foundation treatments on the basis of risks, all the way from structural slab to slab on voids to slab on select fill, slab on soil modified soil, which is moisture conditioning, or slab on chemically or water injected soils. So basically you go floor slab treatment, structural slab, slab on fill, slab on moisture conditioned soils, slab on chemically injected soils. Here's a structural slab system. You go in there, and of course you put your foundation in, and you have a structural slab. This is supported above grade. You got a void underneath it. Could be totally, like a crawl space. That's for a big structure. You can have a big project where you got highly expansive soils. You don't want to the slab be in touch with the highly expansive soils. So you have this kind of crawl space looking thing, or you go put the Tiltwall building foundation, the slab on void boxes. These are cardboard void boxes. The thickness of it is twice the amount of the PVR or potential vertical rise, which I want to talk about it in a minute. You got to put void box in the grade beam as well as in the floor slab areas. So that's kind of like floor slabs throughout the whole floor slabs and the grade beams. You put this storm cover on top of the void boxes before you put the steel in so that the steel doesn't punch through the void boxes. So that's you put the storm cover. These are void boxes in the grade beams. You can see them with a storm cover on top of it. For the vapor barrier, the steel, and this the vapor barrier over the wood boxes. Start pumping the concrete after you put the steel in. And you pour the concrete for all the strip footings, or these are the void boxes here. More void boxes. Again, you got void boxes in the grade beams as well. Around the piers. Yeah, the thickness of the void box is twice as much as the PVR. Isolated plumbing from the expansive soils. In some parts of Texas, we've got such highly expansive soils, such as San Antonio and Austin and Dallas area, especially. You put your plumbing in certain type of void box type systems so that the expansive soil would not lift it. and it start pushing against your fixtures such as sinks and toilets and stuff. I had a case in near Dallas where everything was moving up because the expansive soil was pushing against the plumbing. Void boxes should be twice as much as the PVR. Potential vertical rise is the ability of a soil expressed in inches that can swell, how much it can heave, shrink and swell actually, for a specific area. It's the map I developed for Houston. For example, if you go out there and start building a Tiltwall building out there in Brookshire, your PVR is about 1 to 1.5 inches. Go out there and the full share is 2.4 inches. You go out to Rosenberg, it's about 5 inches, 6 inches. You go to Great Wood out there, 6, 7 inches. You go to Pearland, it's about 5, 6 inches. And so you go Leak City can be as much as 8 inches. You go to Baytown, 4 or 5 inches, 6 inches. Crosby, 5, 6 inches. You go out there to Kingwood, depending where you are. If you're near 59, you can have 3, 4 inches of movement. You go near Lake Houston, PVR would drop to 1 inch. And so you go inner city type stuff. Out there, Westview, Bel Air, Tanglewood, you're gonna have 4 or 5 inches of PVR. So PVR for Tiltwall building should be less than 1 inch for your floor slabs. So if you got highly expansive soils, you can remove the expansive soils, put it back with select fill. So if you got a soil with a movement active zone of 10 feet and a PI of 60, you got to remove 7 foot of soil to get a PVR of 1 inch. And that's not happened. I did a Walmart out there, and I remember near Dallas, and where they took out 7 foot of soil throughout the whole site, and put select fill in there and build a Walmart there. Select structural fill, of course, soil with liquid limit less than 40, PI between 12 and 20. This is the kind of soil you want to put underneath your floor slabs so that it does not heave. Sometimes because of the elevations, you may have to dig a hole, start bringing select fill in there, and compact it with the sheep's foot, and bring it out of the ground. So if it's a dog high building, you have to bring it all the way up. It's going to be your pad. You got to cut it nice and vertical. Can't let it sit very long, otherwise it's going to go bad. This is your pad in here, really nice work. This is your select fill compacted. You compact it with a sheep's foot. You crown it. You seal it with a steel drum roller. So when it rains, water doesn't get in there. It will shed off of it. You seal it. So if you got a Tiltwall building, this is your pad in here. You got to run density test every lift at 50-foot spacing. Make sure the density passes. Got a typical makeup, of course, on a Tiltwall building. You got the panels going around the perimeter. You got interior drill piers or spread footings. Isolation joints between the slab and the columns. Here's another one where you got the columns, you got the panels going all around. Slab with moisture conditioned soils. I mean, we see that a lot on a lot of the projects where you dig out your detention pond and moisture condition that soil. You compact that soil at optimum plus 4%. You put it in 8-inch lifts. You got to keep that moisture constant. If you let it sit dry in the middle of summer, you're going to lose it and your slab's going to heave. And that has happened to a lot of people I've seen. I was just looking at 4 Tiltwall buildings in Dallas, Fort Worth area, where they did moisture conditioning, but by the time they poured the slab on it, they had lost all that moisture and the slab started moving. So you run a Proctor test. This is your optimal moisture. That's your dry density. You compact the soil at optimum plus 4%. You compact at 15% moisture, 95% standard Proctor density. Okay. So you dig a detention pond. And as you dig the pond, you bring in the soil, try to build your pad. You add water to it. Keep it wet. You compact it with a sheep's foot. Cover the area after you moisture conditioned. I say within 7 days, uh, with plastic sheeting, because you're going to lose moisture. So you got to cover it up. Otherwise, you lose it. And if you lose it, your moisture conditioning doesn't work anymore. Chemical injection, again, if you got expansive soils, you got to do chemical injection. That's another option. Basically, clay particles, they got negative charge. Water has got positive charge. You do what's called cation exchange. You reduce the negative charge in here by adding chemicals such as, light grade sulfuric acid, makes these negative charges go away and it doesn't heave as much. So basically, chemical injection removes the monovalent cations such as sodium and potassium, replaces it with divalent cations like calcium. So you get the chemicals in this tank. You inject it. This is a sienna plantation. Injected to a depth of 10 feet in Houston, 15 feet in Dallas, San Antonio, and Austin. Inject 24-inch spacing usually. These chemicals go all the way down to a depth of 10 feet. Inject it. That's the hole. Soils where chemical injection usually more effective are the ones where they have a lot of cracks in them. Like in the summertime, the soil shrinks. Basically, the chemicals can travel easy. See the cracks in here? This is A-leaf area near Houston. See all these cracks? Again, after chemical injections in Houston is about 10 feet. Dallas, San Antonio, Austin, 12 to 15 feet. Vapor barriers, we recommend something like a 10, 15 mil vapor barrier. You put it on top of your pad, you put your steel in. Use a 15 mil barrier. Drainage, got to make sure you got positive drainage around your building. We don't want water near your building. You get a 5% slope in the grass, 2% in the concrete. When you pour, of course, your slab and stuff, you got basically a slab closure strip area. So this is your regular slab that you pour. You got a space between your piers where your panel is going to go, and the slab's got closure strip. And you can see it over here. Your piers going over here. That's the space. Your panels going up in here. You got the steel from panels coming in, down into your slab. You pour your closure strip. See again, the steel from the panels like this, extend out. That kind of keeps your panels together, gives the whole building stability. All these soils in your closure strips got to be, soft stuff removed and compacted lifts all the way to the top, 95% standard Proctor density. Got to compact all this, put your vapor barrier in, and then you compact it. You cannot have soft soils in here, otherwise it's going to settle. So you got the steel coming in, connects to your panels. Yeah, concrete coming over here. You got your steel. You got your vapor barrier. You pour your concrete, your closure strip. Soil underneath it got to be good, nice and hard. If you don't compact it, it's going to settle. Here's your closure strip that's settled. Right here too. You had to jackhammer it. Go back in this case, they went back in, put cement and stabilized sand. Put the steel in. Pour it back in. Floor slab loading. Typical, shelf loading is 150 to 200 pounds per square foot. Your column loading and the perimeter loading from the tilt wall panels and stuff. You got a service load, usually about 175 kips. Factor load for factor of safety, you can use 215 kips. Interior column loading, 100 kips. With factor 150, you got a 1.5 factor in there. The kind of foundation you use is drill piers, strip footings, spread footings, auger cast piles. That's typically what we do. Got expansive soils. You use drill pier foundation system here. It's a pier cap. You grout between the panel and the foundation. This is your slab in here. Yeah, you got a reamer rig and auger rig when you drill stuff. You drill the hole for the piers. That. Start drilling. It's auger rig. That's the reamer. The reamer. You make a bell for this thing. Got heavy loads. You open up your reamer. Make sure it opens up properly. You got to measure it as part of your observation in the field. Make sure your drill piers are clean. No loose materials. No more than 3 inches of water should be in it. You put your steel cage in it. Start pouring concrete. Make sure it doesn't hit the sides. The way you determine your pier depths is scientific. Here's some concepts. This is your pier depths all the way down here. You got a basically active zone depth, which is calculated several ways. When you hit a sand layer, you hit the active zone depth. When you hit a rock layer, that's your active zone. 2 foot below the lowest root fiber. When the change in suction is less than 0.27 pf. When your liquidity index becomes vertical, the depth of slicking sides, and when you know historical water table. Soil suction, we do that in a test in the lab. Basically, as to free energy state of the soil. Soil suction is described as the ability of an unsaturated soil to attract or retain water in terms of pressure. The PF is expressed as log of 10 base 10 of height of centimeters of water column that the suction would support. So you got basically your active zone, but that's not the movement active zone. That's just the moisture active zone. Then there's this thing called zero movement line or movement active zone. That's about 10 feet in Houston, and Dallas, San Antonio, Austin is about 12 to 15 feet. Then you got to anchor that pier below that to resist uplift from the expansive soils. That's the anchor zone. And you don't count on the belt to resist uplift because by the time the belt gets engaged, that the panel has moved 2-3 inches up. So you don't count on the bell to resist uplift. And so where you got a tree, of course, before, the active zone depth is deeper. So you have to check your pier depth for compression loading. Yes, the end bearing, and of course, skin friction for compression. You got to take that, make sure you got a proper, bearing capacity there. And of course, you got to resist uplift. You got a skin friction above the zero movement line that you have to counter with the anchoring depth. You don't count on the belt to resist uplift. So that's how you determine your pier depths. So if your zero movement line or movement active zone is 10 feet, your actual pier depth is twice as much as that. It'd be 20 feet. That's how you determine it. These are some panels out there near Pearland, sound walls sitting on piers, and you see expansive soils grab the piers and push them up. So you got to be piers, it's got to be deep enough to resist uplift. There's a procedure by Foundation Performance Association that you can download if you're a member of F.PTI, and you go through calculation. You put your soil layer information in, your suction levels and loading, and you can check your piers against, in this case, against uplift. and of course downward movement, and make sure it meets that. A connection between the piers and drill footings. A lot of times, some of the structural engineers says, "Oh, we need to have good connection." Maybe have steel between the piers and or foundation and the panels. I don't see that. Basically, we see a steel plate where your piers are, and you put your column, your tilt wall panels directly on top of it. It's kind of like a friction connection. The panels sit on top of the piers. These are the piers. Sometimes I see these little guided steel plates in here, and they're bolted to the top of the pier. Got to make sure your panel sits in the right place, like that. So the panel sits there, and they're bolted. See that? These are connections between the pier or spread footing or strip footing and the panels. But there's no really, like we don't have steel from the piers going into the panels, into the panels. That's just, we see the connections there. There's no connection between the drill piers and the panels. Here's a strip footing foundation. If your soils are non-expansive, you would use strip footing. These are your panels out here. You have to grout underneath the panels. Otherwise, it's going to settle. So as soon as you put your panels on top of the strip footing, you got to grout this area here. That's your pour strip area. Got to be nice and compacted soils. There's another one. That's an at grade panels. The other one was kind of like a dock high. And then again, this is a grout area. So if you got a building like that, you pull your strip footing. That's your strip footing here. You line up your panels, put them on top of the strip footings. There's no connection between the strip footings and tilt wall panels. Once the panels are set and aligned, space between the footing and the panels should be grouted. Otherwise, you have settlement problems. That's the grout right there. Like that. Precast panels. Some of these projects, they don't pour the panel right there. They just bring in the panels, precast panels. They line them up like that on top of the strip footing or spread footing. Spread footing foundations on non-expansive soils. Again, this is your spread footings, your panels sit on top of that. You dig your spread footings, put steel in it, or concrete. There's no connection between the spread footing and tilt wall panels. You set the panels directly on top of the on top of the spread footings. Like that. There's the gap between the panels. That's your spread footings. That's the corner. And you put the panels on top of it. You do the bracing. Auger cast piles. If you have areas where you have a lot of sandy soils or shallow water table and expansive soils, you got to go with deep foundation. But because of the water and sand, you would use auger cast piles. So you got a tilt wall building. You drill these holes. You got an auger in here. You drill into the ground. Auger cast. There's a hole in between here. You push the grout through it. That's the head of it. And you got your steel cage. You push it into the grout. After you drill the hole, you put grout in it. Floor slabs, concrete placement. Once you compact your pad, you go in there and make sure it's nice and compact. Got to be proof rolled. Density test every 50 feet or so. You got to set your forms, put in your steel vapor barrier, start pumping the concrete in. You got a concrete, hopefully slumped no more than 4 inches. You vibrate it. Make sure there's no voids in there. You can use laser guided screed for horizontal concrete placement. This device really does a nice job of finishing for your parking lot as well as your floor slabs. You use that on a lot of projects nowadays for concrete placements. You go on there, trowel it. Keep your surface of concrete from rapidly drying. That's you got to do a curing compound. Make sure we don't have loss of moisture, otherwise you're going to get curling. So the way you do the basically curing starts immediately after the final trowel. Cover the concrete with a membrane or spray with the liquid curing compound. I see that the spray is what's used most of the time. I mean, you can put blankets like that on or plastic sheeting, or you got to do the spray. Do a lot of spray. Got the whole thing got to be pretty white and keep that moisture in. Otherwise, you're going to get curling or develop plastic shrinkage. Basic contraction due to loss of moisture from concrete during the plastic state occurs in concrete is being placed or finished, affected by evaporation rate, high concrete and air temperature, and low relative humidity and high wind speed. You develop shrinkage cracks. These are shrinkage cracks. You don't want that. All these shrinkage cracks, you got to do proper curing. You don't want the shrinkage cracks. Keep the slump less than 4 inches. And of course, put control joints. So once you pour that slab, you got to go in there, put control joints, I don't know, 6 to 12 hours or 6 to 18 hours after the pour. You saw cut it 1/4 of the slab thickness. So if your slab is 6 inches, you go do a saw cut 1.5 inches deep. You put them at 15-foot spacing, not 25 foot, not 20 foot, 15 foot. You saw cut it, tells the concrete where to crack. Go 1/4 of the concrete thickness where your saw cut goes. Yeah, this is the control joints. You want to keep them in 15-foot spacing. You saw cut it 1/4 of the slab thickness, and it cracks directly underneath it, so you don't develop a bunch of shrinkage cracks. It's kind of a finished floor in here. You can see control joints in your store. The spacing between the control joints should not exceed 15 feet. This distance should not exceed 15 feet. We see a lot of these slabs with 25-foot control joints. It's not acceptable. The control joints, expansion or construction joints, like that. You got a steel going in there, the dowel. That's your expansion joints. Curling, caused by a rapid drawing of the upper half of the slab. The upper half of the slab shrinks more than the lower. This is therefore causing the corner to lift. So you get curling due to fast curing of that concrete in the upper section of it. So you got to be careful. As soon as you pour that concrete, put the curing compound on it. That way you reduce potential for curling. The steel should be the top 1/3 of the slab or at least half of the slab. And so the thicker the slab is, the less potential for curling. That's the curling, what happens on your joints. You develop voids underneath the concrete. As the concrete lifts up like that, curling usually is about 0.25 inches. It could be as much as 1 inch curling. Here's a kind of a typical slab out there we're looking at. Project in Arizona. And we saw the curling out here. Put a 4-foot level on it. And you can see it's not level. And see it near the joints. There's curling going on. Some of the joints, because of the forklifts, they start going bad, the wear and tear on them. You can see the space, that's the curling space. These are the joints open up. You can see the curling here. And you can see the forklift going through it and making that noise. You hear that? Boom, 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 boom. So as the forklift goes through it, it makes a noise. There's a void underneath the slab. It's coming up, curling up. So you got to go in there and inject it. You could use polyurethane or other type of material. Inject it to fill that void. And then you're going to have to basically grind the top of it to make it level. So how to basically reduce curling is use a thicker slab, cure the concrete good, make sure you cure it right away, keep controlled joints close together, use a slump of 4 inch or less, put the steel in the top 2/3 of the slab. The remedy, to inject grout or polyurethane underneath the void at the corners, nail down the concrete slab at the joints, saw cut diagonal, several feet back from the corners to allow the crack for it to stop to crack and settle down on the ground. Floor slab construction after raising up the Tiltwall panels. If you want to control the temperature and the rain and stuff like that, you can set up your panels, you lift them up, but you don't pull your slab. You put your braces in, put your roof in, you cover it up, you basically seal your slab. There's no rain, you don't have to worry about that, sun and all that stuff. You remove your braces and compacted soil, of course, is your pad. You pour your slab, there's no closure strip, it's nice and clean. So you don't have to pour your slab first, but so you can pour it after you set your columns in and put your roof in, and after you're setting up all your panels. So columns, of course, you set them in. You're going to have joints, sometimes diamond shape. Contractors got a hard time coming up with a diamond shape type deal. Most of them are going circular nowadays. You got your anchor bolts for your columns. That's an isolation joint between your slab and your columns. That's the top of your piers. See that? A lot of people are going with a round cardboard type joint. Floor slab loading. You go inside some of these Tiltwall buildings. They got all these shelves out there loaded up. All kinds of loads, and they got forklifts going all over the place. Boxes. Forklifts lift stuff up. A lot of boxes. Heavy industrial loading with the forklifts. Heavy loads like that could be sitting in there, 3,000 PSF loading on the floor slabs. Panels, once you pour your slab, you set the forms for your panels. You got to put bond breaker between the bottom of the panels and your floor slabs. You put your steel in, you put in chairs. Between the steel and the concrete slab, pour your concrete, your panels, vibrate them. Once your concrete hits a certain strength, you start lifting your panels, usually within 7 days. Sometimes you get early strength concrete, you pick it up within 3 days. You finish it, trowel it, place a bond breaker between the panel and the floor slabs. You got to put a bond breaker here. You do a lot of times, you do the spray kind. You got to wash it off, from what I understand. Once your panels are ready, which is usually about 7 inches thick, the Tiltwall panels, start lifting them with a crane. I don't like the crane inside the building when you lift them. Those outriggers put a lot of stress on the floor slabs. You do it from the outside on soils. You lift them up, you stand them up, put in the braces. These outriggers, you're going to put a lot of stress on concrete unless they're designed. We don't recommend placement of the outriggers on the concrete. Let's see. Let's see any questions in here. I got some questions. So the outriggers put a lot of stress on concrete. There's this guy over here. They're putting the crane inside the building, and you start lifting the panels. These are the outriggers. Again, in here you got the crane inside the building. Do not put cranes on the slab or paving unless it's designed for it. Early concrete breaks, of course. You make concrete cylinders, and every 50 yards or so, 3 layers, you rod them in. These are your cylinders on the job site. You leave it there 24 to 48 hours and take them to the lab. You break them. You can get early strengths. When you get the early strength, talk with the structural engineer, start lifting up the panels, put them in on top of the piers. Tiltwall panel separation. You can see the separation in here. You got voids in here. You put joint filler in it. In the panels. Connections. Some structural engineers like to put in connections between the panels to keep them together. They kind of bolt them in with steel plates like that. Some people don't. Some people just put them on top of the piers and then connect them at the roof. So these are some of the steel plate connections. Here. Wall bracing. When you lift up your panel, you need bracing. They're anchored on the bottom here and the top. It's screwed in there. When you don't have slab, you're going to have to anchor them on the bottom in the soil right here at the top. See more bracing. The kind of screwed right there, and then the bottom screwed right here. Parking lot. If you got expansive soils, let's say you're doing a Tiltwall building out there in Rosenberg, you got to lime stabilize that subgrade. Use, basically lime slurry type B. You got to cure it for 24, 72 hours. Gradation, 85% should pass 1.75-inch sieve. 60% should pass 0.75-inch sieve. Compact to optimum plus 3%. You remove grass and stuff like that. You bring in your lime. Start spreading it. Start mixing it. Add water if you need to. Let it hydrate. Break down that clay. Cure 24 to 72 hours to obtain optimum hydration. You pulverize it. That's your original clay. After you lime it and pulverize it, it becomes like granule material. So you got samples of that, run it through sieves. These are the sieves. Make sure it meets the gradation. After you pulverize it, compact with sheep's foot. You seal it with a pneumatic roller. That's your sheep's foot compacting. You seal it so water doesn't get into the soil. That's why you seal it. It's a steel drum roller. Compaction, you run density test every 50 feet. It's a nuclear gauge. Every density every 50 feet. Density, you do depth check every 50 feet for lime stabilization using phenolphthalein, and gradation every 50 feet. Depth check, you just dig a hole and you spray phenolphthalein in there. It turns purple. Tells you the depth of stabilization. So if your stabilization is supposed to be 8 inches, you don't want it to go 10 inches. That means you didn't use lime at a deeper depth. So that means you don't have as much lime in there, concentrated. So that's fails. So you got to make sure your depth of stabilization is not exceeding what the specs call for. So if the specs call for 8 inches of stabilization, this thing should not turn purple below 8 inches. So you check it. After your lime stabilization, you put your steel in. You don't want to have these shrinkage cracks. That's too dry. Too dry. Once you put your steel in there, you got to pour that concrete right away. If you develop shrinkage cracks like that, you're going to have to remove that steel, add water to the soil, put it back in. These are too dry. Not acceptable. Not acceptable. That's why you get a bunch of cracks in your concrete. The way you do mixes on for lime stabilization, you add enough lime to get your PI less than 20, or use heads of grime. You want to have your lime stabilized soils at a pH of 12.4. This is a better system. You run a pH test. This is the amount of lime you add, and that's your pH. Once you get about 12.4, you need about 6% lime in here. I usually add 1% to it because of the waste and stuff. So if you need 6%, I specify 7%. Or you can use basically percent soil finer wet method here and PI and go through these curves. And if your PI is 40 and you got percent binder of, let's say 70%, you need 6% lime in here. If your soils are sandy, use lime fly ash. Use a type B. Lime fly ash could be type C or F. And compacting within 2 hours, no more than 6 hours after adding and mixing the last stabilizing agent. You don't let it cure. You add the cement or lime in there. Cement or fly ash in it and compact right away. So first you go lime stabilize the sandy soils. You dry it up. Bring in your fly ash or cement. Then add water if you need to. pulverize it, compact within 2 hours. And 6 hours, no more than 6 hours after adding the fly ash. Compact with a sheep's foot. Run the density test every 50 feet. Make sure it's nice and compact. Check for sulfates. So if I'm doing stuff in Fort Worth or places near where you have sulfates, these yellow areas by TxDOT shows maps and counties where you got sulfate. And if you have excessive sulfate, you're going to get sulfate heave, and you're going to have problems. And of course, too much sulfate may affect your steel and the reinforcement. So you got to make sure in certain parts of Texas, if you have high levels of sulfate, you got to test for it. And if you got, you cannot do lime stabilization or lime fly stabilization. So typically, the sulfate occurs, induced heave occurs in clays. If your pH is greater than 10.5, usually soluble sulfate is really more than 8,000, and moisture is present. And the clays mixed with the lime or cement, pH is increased from natural values of 7.8 to about 12. Sulfate-induced heat can occur. This is some asphalt paving that are going through sulfate heave. That's in Friendswood, near Houston, which is roadways all heaved up and cracked up. These are sulfate-induced. These are salts that got sulfate in them. So if soluble sulfate level is less than 3,000 parts per million, you got low risks. You don't have to do anything. Between 3,000 and 5,000, you got excess water must be added. You got moderate risk. Excess water needs to be added. Soil got to be compacted, 3% above the optimum. The initial mixing should be conducted at moisture content 3 to 5% above optimum. If your sulfate is between 5,000 and 8,000 parts per million, you got moderate to high risk of sulfate heave. Excess water must be added during the mixing. Water should be used to up to 5% above optimum for compaction. In addition, sufficient mellowing time of 6 days should be allowed before final mixing. If your sulfate is above 8,000 parts per million, you don't do any kind of lime stabilization or cement stabilization. So you're going to have to dig out that soil, bring in soils that's not have sulfate in it, then you can stabilize it. Or you don't stabilize it at all. I was in Fort Worth, a few months ago. They had a huge building out there, and none of the paving had any stabilization. They just compacted it and put concrete on top of it. So they didn't do any stabilization because of the high sulfate. Concrete placement, so you compact that soil subgrade, you set your forms in, you get your dowels in, make sure they all are straight. You got your expansion joints. We like your expansion joints about 80 feet apart. Your dowels. You put chairs. If you have wet area, you put some lime to dry it up. This is your dowels. Expansion joints, 80-foot spacing. They got to be nice and straight, not bent. Start pouring the concrete. You got your laser screed coming in. Finishing it. Make sure your concrete stump doesn't exceed 4 inches. You vibrate the concrete as you're pouring in. Pour in pour strips to allow for shrinkage. Got to go in there and put control joints in within 6 to 18 hours after the pour. You trowel it. Start saw cutting it. You put control joints in at 15-foot spacing, not 20-foot spacing. These are your control joints. You tell the concrete where to crack. It should not exceed 15 feet. Going to have nice parking lots. Otherwise, they're going to have cracks if they have control joints far apart. The thickness of this concrete depends on the traffic loading. Typically about 8-inch concrete for your parking lots. 6 to 8 inches. Minimum concrete pavement thickness. Loading ramps. You're going to have some loading ramps there. You got to design them for bearing capacity, lateral pressures. Make sure all the soils underneath the loading ramps are compact 95% standard Proctor density. So we got to design them for bearing capacity, lateral pressures, soil backfill type, and compaction. Compaction should be 95% standard Proctor density. Backfill, use select fill. Soil with liquid limit less than 40 PI between 12 and 20. You design it for lateral pressure of 0.7 times gamma H of the soil, whatever that is. You know, if soil is 125 pounds per cubic foot, usually design it for about 103, what we call 103H. Bearing capacity, you know, you want to have enough bearing capacity, hopefully more than 1,000 pounds per square foot. Truck wells, you go out there and excavate, and the trucks go down. Here, you're going to have to worry about soft soils and groundwater as you do this for your truck wells. When you pour that concrete, make sure you got joints in it. Otherwise, it's going to have a bunch of cracks in it. You want a joint spacing, control joints of about 15 feet. For your truck wells, you need bearing capacity, lateral pressures, dewatering recommendations, and compaction. Compaction is going to be 95% of standard Proctor density. If you have shallow water table or perch water table, you're going to account for that. That's it. So if you got projects, send me some pictures. Love to have some pictures on your projects, on Tiltwall buildings. You know, again, I love these buildings. They're very nice. If you got pictures of failure and stuff like that, I'm doing a whole presentation on Tiltwall building failures. So I appreciate any pictures you send me. This presentation is going to be on YouTube. Geotech Engineering and Testing. There's like 35 programs on there. You can go watch it and send us an email. We'll send you a PDH on that. You can contact me. My email is de@geotecheng.com, 713-699-4000. There's a poll in here. Tell us what you think of the program. Let's see. I don't know if it does work or not. Yeah, I'm not sure the poll is working, but if it does, go ahead and respond to it. We're going to have a bunch of other programs coming up. If you're listed here, you're going to get our emails on some of these webinars that we're going to be doing. Again, I'm going to be doing one on tilt wall building failures and pavement failures for tilt walls. I'm just working on it right now. It's not ready yet. You're going to get your PDH hour for this today. So it's very important on these tilt wall buildings to do a proper geotechnical work. This is your original design. If this starts failing, that's going to cost a lot of money. I've been spending a lot of time across the state on these tilt wall buildings that are failing. A lot of them bad design and shallow piers and wrong type of soils under the floor slabs. Or if they did moisture conditioning, there was no moisture conditioning. Soils are dry and they're heaving up. So there's a lot of problems like that going on. Any questions?